When we take 3 dimensions, if we take, for example, a point is, for example, we have the x-axis, then the point we say x equal to a is a point on x-axis. We say it's 1 dimensions. For example, I am here, this is my xy plane, and I take here x equal to a, and this is my x-axis as my y-axis. When this x equal to a is a line passing through the point x equal to a, this is my, here is my origin, and this is my line. X equal to a is now here a line. X equal to a was here a point, and here x equal to a is line. Now in 3 dimensions, if I take here, this is my z-axis as my y-axis, and here is my x-axis, and we take here x equal to a. Now x equal to a here in this case is the plane, and in this plane we say the all values of y and all values of z, they are equal to 0, and we can say this is my plane here parallel, this is my parallel to z-axis, is parallel to y-axis, and this is my plane, and this plane I say x equal to a. Now the value is same, we say x equal to a, but in 1 dimension is the point, in 2 dimensions is the line, and in 3 dimension x equal to a is plane. So just to give the idea of 3 dimensions, I have used this one. Now for example, if I have a point, I say I can draw lines, infinite number of lines passing through this point. This point is any point. We say if I'm having a point and we say we have the vector, as we see in the equation of the line, we can say there is only one line we can pass through this point which is parallel to this vector. Or we say having 2 points, we can have only one line passing through these 2 points. So similarly, when we say we are having a point and we have the plane, we can have the 2 points. We can have many planes passing through these 2 points. Or we have a point, there are many planes passing through the point. But when we fix this one that we are having here, for example, this is my plane, and here is also another plane which is parallel to this one. We're having here another plane parallel to this one. So we can get a, and so on. But here we're having a vector which is normal to the plane. This is normal to this one. Also the same, we're having here this normal vector. Also same, we have this normal vector. This same vector n. And this is normal to this plane, this is normal to this plane, this is normal to this plane. How we can distinguish between them? We take a point in any one of the plane. We say we take a point at this point in this plane, and this is a vector normal to the plane. So now this plane is fixed. As we fix the point and a vector, we get fix a line, and this was free that we can get many lines from the point. Similarly, there can be many planes which is they are parallel planes, and we have the same normal for that one. But when we take a particular point on a plane, then we say we are having here number 1 a point on the plane, and number 2 vector normal to the plane, vector normal to plane, and that will have a unique plane. That's the plane we'll get. So we use this idea that we are having a point on the plane and we have vector normal to plane. With the help of this one, we can derive the equation of the plane. The equation of plane, as I said, we need 2 things: a point and a plane, x1, y1, z1, and normal vector to the plane. So we can see this is any point, another point in the plane, and p anywhere in the plane. So we can get here vector in the plane p1p. The vector p1p is equal to x minus x1, y minus y1, and z minus z1. This is any vector in the plane. We have vector normal to the plane. Vector normal to plane, we are having the coefficient of the vectors are a, b, c is a vector. So we say this vector n is normal to the plane. So this means this vector n is perpendicular to the plane, any vector on the plane. For example, this is my plane, and I take this one as a vector normal to the plane. So you can take any vector here in the plane, then this is normal to that plane. I take any vector in the plane, then this vector is normal to that plane. This vector is normal. So I can take this vector. This means this vector is normal to the plane. So this vector is normal to every plane. So we are having these 2 vectors. This vector in the plane, this is normal to the plane. So we use our idea of the dot product. Then when dot product of 2 vectors, when they are orthogonal to each other, then this is equal to 0. So we say n is a normal vector, n is normal to the plane, and we say the point v1 p is a vector in the plane, is vector in a plane. So here we say normal vector, or we say is perpendicular to the plane, same thing. So when we having this vector, so these two vectors n and p1p are orthogonal to each other. When they are orthogonal, when we have the property of the dot product, then n dot p1p, that must be equal to 0. So we are having this one, we put the coefficient of this one, here vector n is equal to this a, b and c, and p1p is equal to x minus x1, y minus y1, and z minus z1 is equal to 0. So we multiply them, we get here a x minus x1 plus b y minus y1 plus c z minus z1 is equal to 0 is equation of the plane. Is equation of plane, and we say the equation of plane which contains point P, and this is with the coefficient with the values x1, y1, z1, and vector n. And vector n is having the coefficient a, b, and c, and n is normal to the plane. So this may give me the differential equation. They give me the equation of the plane, and this is my equation of the plane. So I just multiply them, and we get here ax plus a minus a1x minus a1x1 plus by minus b1y1 plus cz plus we are having here the a1 here is plus cz1 minus cz1 equal to 0. Or I can write this on ax plus by plus cz is equal to a1x x1 plus by1 plus cz1. We say this is equal to ax plus by plus cz equal to d, where I can just define my d. My d is equal to ax1 plus by1 plus cz1. So this is my standard equation of the plane. We can write like this one is standard equation of the plane. Is equation of plane. We can just have the equation. We can give any point, and we are given the normal vector. We can write equation of the plane. So this is the idea. We can use it where it's very easy, and we actually used here the idea of the dot product. And this is my vector equation of the plane. This is my vector form of the equation of the plane, and this is a Cartesian form of my equation of the plane. And we're having here two things. We're having here the given the point, and from the point and from given vector we can write equation of the plane. I give the example to explain you further, and that how we can apply this one to get the equation of the plane in general. So I'm having here an example for you. We are given find the equation of the plane. This is my equation 1. I can write this as my equation 2. So I'm just having want to find the equation of the plane. When we are using here, the point is given to me minus 11, 4, and minus 2, and given the vector, the coefficient are 6i minus 5j minus 6k. So solution of this one, we apply our equation here. That's here the coefficient. I will take the coefficient vector n with having the coefficient a1, a2, and a3, and I take the point P as x1, y1, and z1. So my equation will be a1 x minus x1 plus a2 y minus y1 plus a3 into z minus z1 equal to 0. Now I've given here a1, a2, a3, that's 6 minus 5 and 4. So I get here 6 into x minus x1 is x minus plus x plus 11. Then we're having a2. What's my a2? a2 is minus 5. So his a2 is minus 5 into y minus y1. y1 is 4. So get here y minus 4 plus when we get a3 is minus 1. So minus z minus z1. z1 is equal to minus 2. Minus become plus. So this is equal to 0 is my equation of plane. So it's very easy, just making substitution. we get the result of the equation of plane. Just we need a point and we need a vector. So we are given here the point and we give here a vector. We apply that one. This is my point and this is my vector. I apply that one and I can get here my equation of the plane. So all what we did, we just make this my vector and this my normal vector and this is my point. We use this one here. We take this one as a point and this is a vector. We make the substitution. We can simplify this one and we can write if asked in the standard form of my differential equation. This is a Cartesian form of a differential equation.